All right, everyone, welcome to this video where I will go over the entire Unit 1 study guide. Let's just dive in. I'm going to skip the warm-up for now and come back to it. And I'm just going to go ahead and jump right into this mind map. Unit 1 is about polynomial and rational functions. And if we understand both of those, then we understand all of Unit 1. So let's start by defining a polynomial. Well, a polynomial is going to have numbers as exponents. Okay, so we are not looking yet at exponential functions, which have exponents or variables as their exponents. And polynomial functions are continuous. I am terrible at spelling. Not even sure that's the correct spelling of continuous, but it means that there's no holes or vertical asymptotes inside of a polynomial function, right? If we do not restrict a polynomial function, the domain is always going to be negative infinity to positive infinity, unless we restrict it and say, oh, well, this only exists when x is greater than or equal to -4 or something like that. This would be a restricted domain, but without those restrictions, the domain of a polynomial function will always be negative infinity to positive infinity. Polynomial functions are given to us in standard and factored form. These two forms help us determine the degree of the polynomial. So if I'm in standard form, the degree is pretty easy to find. Say I had something like, something like this. The degree is just always the largest exponent. So here this would be a degree of 5. In factored form, the degree is always, we're going to have to add these up. Let's say I had something like this. Times x minus 5 to the third. Okay, well, I'd be looking at this, and I'd say the degree here for this x is 1, so I'd have 1 here. There's a 1 here, but this is already an x squared, so there's 2 here. And then this is to the third degree, and I would add these up, because if I converted this to standard form, my leading term would have a coefficient of 6. So the degree is equal to 6. Now, you could always convert from factored form to standard form by distributing, and I don't know, what you're erasing and what you're just following along with. Sorry, I'm doing so much erasing. You could always convert from factored form to standard form, but I'm not sure that's necessary. Now, you can convert back and forth between standard and factored form. All right. If I want to convert from factored to standard, I want to go in this direction. It's pretty easy. I just distribute, right? X times x is x squared. X times 7 is 7x. 4 times x is 4x. 4 times 7 is 28. Combine like terms, I get, now I'm in standard form. And you can see, look, the degree here I can see in standard form is 2. And in factored form, I would have had 1 and 1. 1 plus 1 is 2, so the degree is 2. I can see it both ways. All right, now imagine I wanted to go from standard form to factored form. And I won't give an easy one. I'll start with a more difficult one. Let's say it has something like 2x cubed plus 10x squared plus 12x. Well, I'm going to start by factoring out my least common multiples. I can see that all of these have an x, at least one x in them, and they're all divisible by 2. So I can factor out a 2x. And so I'm really dividing each term by 2x. So this here I'm left with x squared. Here I'm left with 5x And here I'm left with 6. And now that I've pulled out that 2, I can ask myself now, because this is in the standard form of a quadratic, I can say what multiplies to C and adds to B. We get 2x times x plus 3 times x plus 2. Notice once again, the degree in standard form is 3. The degree in factored form is also 3. So factored form is helpful for when we want to find the zeros of the function, because now I could just set each factor equal to 0. And I could solve for the zeros. I get x equals 0, x equals -3, x equals -2. And so that means that this polynomial function intersects with the x-axis at 0, -2, and -3. We'll talk a little bit about end behavior in a second. So this graph would look something like that. Okay. All right. I'm getting a little ahead of myself. Let's back up. So standard and factored form. Most of you already know that, and you're probably bored out of your mind, but it never hurts to touch on the basics. So why did I spend so much time talking about the degree? Because the degree of the polynomial determines its end behavior. So if the degree is odd, then the end behavior is going to be represented by a linear function. That does not mean the function is linear. It just means the end behavior is linear. So if the leading coefficient is positive, then we're going to get a positive leading linear function end behavior. And if the leading coefficient is negative, then we're going to get negative. So how do I get something that looks like this? It would be odd degree, positive leading coefficient. This would be odd degree, negative leading coefficient. Now, if the degree is positive, or if the degree is even, then we're going to get quadratic end behavior. So something like this, or something like this. Well, this opens up, so this would be an even degree and positive leading coefficient. And this opens down like a frown, so this would be an even degree and a negative leading coefficient. So all of our polynomial functions end behavior is going to look like one of these 4. Now that does not mean that it looks exactly like it. So I could have a cubic function that looks something like this. Well, that is not a linear function, but its end behavior is going to resemble a linear function. So there is a difference between the end behavior representing it and the function representing it. Okay. So that is, what else do we want to talk about with polynomial functions? Well, you should be able to discuss these degrees and their end behaviors using limit notation. So I might say, okay, let's say I have x to the third. Let's just take a simple function, f of x equals x to the third. Well, this has an odd degree, and there's a positive 1 right here. So odd degree and a positive leading coefficient. So that end behavior is going to look like this. And so the way I write the end behavior in limit notation, and I can say is the limit as x approaches positive infinity. Or maybe I should do negative infinity first. So as I head forever in this direction, because x is moved horizontally, what happens to the output? Well, it's heading towards negative infinity. So I can say the f of x is equal to negative infinity. Well, the limit as x approaches positive infinity, so as I head forever in this direction, what happens to the output? Well, it's going up. So the f of x is equal to positive infinity. All right, so that's a little bit about polynomial functions and the high-level understanding that we need to have of them. Okay? Well, the other type of functions that we learned about are rational functions. Rational functions are going to have, we typically write them like this. We can say them as the f of x over the g of x. But they are going to be undefined somewhere. It's a polynomial over a polynomial. Rational functions are not continuous, which is a word I still do not know how to spell. They are not continuous. They're going to have some type of interruption in them. Those interruptions are holes and vertical asymptotes. So let's talk about where these functions are undefined. Well, they're going to be undefined anywhere where we get 0 in the denominator, because you cannot divide by 0. If we get 0 in the denominator under any circumstances, then it is undefined over that, in that spot. All right? And whether it's a hole or a vertical asymptote, let's talk about it. So I wrote vertical asymptote on the right side, but I will start with it. This is when we get something like, let's just say I have 1 over x plus 4. Okay? Well, if I substitute negative 4 into this x, then I got problems, because I'm going to get 0 on the denominator when x is equal to negative 4. So what does that mean? It means that x cannot equal negative 4 because the function will be undefined there. And I'll actually get a vertical asymptote, because a vertical asymptote is going to happen when I get something over 0. Right? When I'm dividing by 0, but I still have stuff up here, whether that's 1, 5, 5x, whatever, anything up top, I'm going to get a vertical asymptote. And those look like this. That means there'll be some line here. Well, I guess I should draw it at negative 4. There's some line at negative 4 that the function literally never touches. It gets infinitely close to that. So it might look something like this. And it's going to get closer and closer and closer to this vertical asymptote, but it will never ever touch it. That's what a vertical asymptote is. Why will it never touch it? Because x cannot equal negative 4. Okay, let's move on to the hole. A hole might happen when I have, let's say, a function like this. X plus 4 times x plus 5 all over x plus 4 times x minus 7. Well, you'll notice that I have an x plus 4 term in the numerator and the denominator. And that's going to cause some problems. When we get 0 over 0 like this, that's going to result in a hole at x equals negative 4. And that's going to look a little bit different. A hole is just a little empty space in the graph. So let's say here I'm at negative 4. This function, we'll just say it's going to look something like this. Okay, where there's a hole there. All right, as I get closer and closer to negative 4, I'm probably approaching some number here, but I'm never going to hit it. I'm never going to hit that point, negative 4, comma 2. I'm going to get infinitely close to it, but I'm never going to hit it. Now, there's one quick exception to this rule. I think it's easiest to see on Desmos. Let's say I have some function, f of x. I should have just used the same function I just had. Equals, I don't know, x plus 4. What did I have? X plus 5. All over x plus 4, what was I multiplying it by? X minus 7. Now, I can see at negative 4, if I'm careful here, it says undefined. Struggling to hold it, but undefined. There's a hole there. All right? Now, what happens if I change these exponents around a little? Well, let's say I make this squared. Okay, what happens in negative 4? I still am undefined. So if the exponents are the same or the numerator is higher of the factor, then we get a whole. But something changes when the denominator of the factor has a higher degree. It goes back to being a vertical asymptote. So this rule is true. The 0 over 0 rule is true unless the degree of denominator of the factor is larger. Then we go back to being a vertical asymptote. And maybe it just helps to write an example. This is going to result in a whole. This is a whole. But the second that this becomes larger, I can make this function a vertical asymptote by just changing one thing. If I change that to a 2, now it's a vertical asymptote. And so we have to be able to remember that exception. All right? And I can do a deeper dive on why that is in a later video. All right, that's a lot of time spent mind mapping. Let's dive into some of these problems. You need to know all of Unit 1. I may end up splitting this video up a little bit. In fact, I'm going to do that. I'm going to end this video here so that you have a mind map video, and then I'll start going through the parts.